Hi and Assalamualaikum. My name is Siti Najwa binti Ramli. My teammate are Dr. Najidah Hambali and Dr. Nurul Nadia Muhammad from School of Electrical Engineering, College of Engineering, UiTM Shah Alam, Selangor, Malaysia. Today, we would like to present our project entitled Modeling and Comparative Study of PID Tuning Method for Time Varying Water Temperature. Introduction. Distillation column commonly used in petroleum and chemical industry. Distillation process also use linear and non-linear model such as ARX, ARMAX, NARMA, NAREX and NARMAX. Many research has been done shows that distillation column best works on non-linear model. Time-varying dynamic behavior is an increasingly essential field that has been developed for the non-linear and time-varying model for water temperature. It helps in prediction of the estimated accuracy. The choice of input data is PRBS, pseudo-random binary signal, as it has full spectrum of amplitude and frequency. Second is the multi-sign signal, M-sign, because it is sensitive, which can detect small changes that occur. The PID controller performance depends on its three tuning parameter, which is proportional, integral and derivative, to reach the transient response performance and robustness. Therefore, PID controller is implemented in the non-linear model for time varying to achieve the conventional control. Problem statement. It has been discovered that non-linear model give better performance and greater presentation compared to the linear model. Unfortunately, there is some drawbacks due to the validity in the input set with the use of a non-linear system linear method. The time-varying distillation column is a device that has non-linear behavior and facing a critical problem such as loss detection that cause it hard to explain the physical mechanism. The distillation control also face some problem and limitations such as difficulty in controlling the process and unsatisfactory control performance. Therefore, analysis on NAREX model of steam distillation process has taken place. The implementation of PID controller is used to control the non-linear system and demonstrate the high controller performance of this project. The objective of this project is to create a NAREX model of SDPP. Next is to estimate the transfer function of the non-linear model, and lastly to analyze the model of PID control of the SDPP. For the methodology part, as you can see, there is a flowchart above. After start is experiment planning. Next is data collection, which is we obtain the highest best fit of the input data of each input. Next is selection of model structure by using the reformulated tangent method. Next is model estimation of the transfer function to be used on the Simulink. Next is the model validation, which is we identify the value of Kp, Ti and Td from the transfer function, and if the model is accepted, implement the PID control so that the final result we will obtain the rise time, settling time and percent overshoot of each input data. For experimental setup, a steam distillation power plant SDPP with a 240 volt was used with a specific sampling time for the immersion heating feature. The MATLAB software was used for plant integration and data collection for modeling purpose. Figure 2 is a SDPP plant that display the critical oil extraction method. Figure 3 shows the PRBS input data graph, while Figure 4 shows the water temperature of PRBS graph. Figure 5 shows the M-sign input graph, and Figure 6 shows the water temperature of M-sign graph. For system identification, NAREX model is chosen model as it has no residual items. For the transfer function estimation, the transfer function is estimated from the input time domain. The number of pole and zero is adjusted several times in the system identification apps so that the simulate transfer function is in the right form. After that, the fitness percentage will be obtained. And lastly, the equation of continuous equation will be obtained to use on the Simulink block diagram. Okay, for the model validation, the mean square error MSE data is used to indicate the fitness of the model. The PID control, which is Ziegler-Nichols and Takashi, are chosen to analyze the difference and to calculate the values of Kp, Ti, and Td of the transfer function. As you can see, table 1 and table 2 is the Ziegler-Nichols tuning rule and Takashi tuning rule. The result was divided into 5 parts, which is the best fit and MSE result, the transfer function calculated, the graph of PRBS input, the graph of M-sign input, and lastly is the tuning parameter result. Here is table 3, which is the table of best fit result percentage and MSE result. Okay, for the PRBS input data, the highest fit data is PRBS with band 0.8, while the least value of MSE is at PRBS with band 0.1. For the M-sign input data, the highest fit data was at M-sign with band 0.8, and the lowest value of MSE was at M-sign with band 0.1. Here is the table of calculated values of transfer function values of Kp, Ti, and Td. The calculated values is obtained by using the Ziegler-Nichols tuning rules and Takashi tuning rules at table 1 and 2 from the previous slide. This page shows the graph of simulated PRBS input data. Figure 7 shows PID control PRBS input 0.1 for steam temperature graph. Figure 8 shows the PID control PRBS input 0.5. Figure 9 shows PID control PRBS input 0.8 graph. From the PRBS input graph, it shows that the least amount of overshoot is on Takashi with 0.5 band, and the fastest rise time is at Takashi with band 0.5. Here is the graph of simulated M-sign input data. Figure 10 shows the PID control of M-sign input 0.1 for steam temperature graph. Figure 11 shows PID control M-sign input 0.5 graph. Figure 12 shows PID control M-sign input 0.8 graph. From the M-sign input data, the least amount of percent overshoot is on Takashi with 0.8 band, and the fastest rise time is at Takashi with 0.1 band. This page shows the table 5 of performance transfer function of each values of each input data. From this table 5, it shows that PRBS Takashi with 0.5 band has the best rise and settling time with 23.32 second and 80.73 second, and a small percentage of overshoot, which is 14.08%. For the M-sign data, it shows that M-sign Takashi with 0.1 band has the best rise and settling, which is 35.59 second and 111.4948 second, and it has a very small percentage of overshoot, which is 18.35% data. For the conclusion, the nonlinear model and PID tuning for time-varying water temperature was presented. High fitness and low MSE results were produced based on various bands of PRBS and M-sign. Data of PRBS with band 0.8 and Takashi with band 0.8 demonstrate as the highest percentage of fitness. The fastest rise time and settling time present by PRBS Takashi with 0.5 band and M-sign Takashi with band 0.1 as the percentage of overshoot of the transfer function is small.